Atoms are ridiculous and unbelievably small. A single human hair is about as thick as 500,000 carbon atoms stacked over each other. Look at your fist. It contains trillions and trillions of atoms. If one atom in it were about as big as a marble,
Atoms are very small.
how big would your fist be? Well,
Dylan with the magical insight there.
about the size of Earth. Still hard to imagine? Let's try something different.
Wow, that's Jesus. Oh wow, look how old this little animation is.
Look at your little finger. Imagine that its tip is as big as the room you're sitting in right now. Now, fill the room with grains of rice. One rice corn represents one cell of your fingertip. Now let's zoom in on the
Can we not? That just sounds like it'd be a pain in the ass to clean up.
rice corn. And now, one cell is as big as the room you're in right now.
Speaking of rice corns, that fusion experiment announcement, ignition, that did you guys remember he used that as an example, a rice corn, as the little pellet, the fuel in the middle?
Let's fill it with rice again. This is about the size of a protein. And now, let us
Look, Kurzgesagt's videos are usually really good, but this is, I don't think this is being very helpful.
fill all the empty spaces between the rice corns with fine grains of sand. This is roughly how small atoms are. What is an
It does paint a physical picture, so it does help.
atom made of? Let us just pretend that atoms look like this for a minute to make it easier to understand. An atom consists of three elementary particles: neutrons, protons, and electrons.
Don't forget the gluons. They glue things together. In a sense, it actually is. It holds
Protons
true.
and neutrons bind together and form the atom.
So I was somewhat joking there, okay? So when we're talking about gluons, we're gonna have to go a bit deeper than what he's showing here. We're talking about subatomic particles there. So I'm not sure if he's going to talk about subatomic stuff, right? We're talking about atoms here. So let's just stick to the atoms and steer away from the particle physics stuff.
Atom core, held together by the strong interaction, one of the four fundamental forces in the universe.
So the standard model, which I just mentioned, particle physics, right? That basically wraps up these three into the standard model of particle physics. And early enough in the universe, these actually merge into one unified force. This fucking thing over here, we have no idea how it fits in with the standard model of particle physics. These three together in the standard model. The standard model is what you call a quantum field theory. But gravity, we don't know how gravity fits in with quantum field theories. People are trying to do it in theoretical physics, but still to no avail. So let's talk a bit about, I guess, these three in this video, if he's going to talk about them.
They are made from quarks and held together by gluons.
All right, so this is particle physics subatomic territory, okay? And so you can kind of see the gluons is what I was just sort of getting at. You've got the quarks and the protons here. Well, this is a neutron. Protons, which are 1 over, they are what we smashed together recently on the 5th of December to get the fusion reaction, PP chain fusion, proton-proton. So
Held together by gluons. Nobody knows exactly how small quarks are. We think they might literally be points, like in
even protons, right? Which is what quarks, what protons are made of quarks. But protons, we still don't have a good estimate on the size or even the mass of these things. So that's interesting to note as well.
geometry. Try to imagine them as being zero-dimensional. We suspect that
Oh yeah, that makes sense.
quarks and electrons are the most fundamental components of matter in the universe. Electrons orbit the atom core. They travel at a speed of about 2,200 kilometers per second.
Wow, this is outdated. Because guess what?
Travel at a speed
They're not doing that. So you can calculate that they have angular momentum, orbital angular momentum, right? Which suggests that they're orbiting. That's why you had the Bohr model with way back, but we quickly realized that is not what's going on. Yeah, 7 years. So electrons are actually not orbiting, right? Even though they have orbital angular momentum, which is really interesting. So what is it? So something to also add in here, the electrons themselves, subatomic particles, also have another type of angular momentum, and that's what we call spin. Okay, so angular momentum generally means spinning things, right? And so we know electrons have spin, but they're not actually spinning. So that might confuse you again. But I brought that into the mix to kind of show you, like, the angular momentum they're talking about here with electrons going around atoms is not what's happening. So you might have heard of the electron probability cloud or orbitals. Well, these are referring to what electrons are really doing. So electrons have this fuzzy wave function, which is, in a sense, not physical, although some people suspect it might be physical. And it's not physical because the wave function is, described by a real and an imaginary number. So it's complex valued. And when you have an imaginary number representing something, well, how do you represent something in reality with an imaginary number? So now you might be confused how real calculations out of something that has imaginary numbers in it. Well, math wizardry, math tricks. But you can get probabilities out of these things, right? And if you go deeper into the framework of quantum theory, it suggests that nature is actually probabilistic inherently. And so what this means, for tying this back to what we were talking about, you have this probability cloud. Basically, the probability cloud is actually the electron is in a superposition of every possible place around in this orbital, and it actually has a non-zero probability of being everywhere, which is kind of weird to think about. So the fuzzy electron probability cloud is much more accurate than thinking about an electron orbiting an atom. It's more like everywhere at once around the atom in a fuzzy probability cloud. Nature is far weirder than how we try to interpret it in our, a mind that evolved on the savannas of Africa to interpret how lions are chasing us and shit like that, right? This is why this isn't making a lot of sense if this is a first to you. These electrons are literally in this fuzzy state of being somewhat everywhere at the same time. If that sounds like craziness, trust me, go learn physics. It gets even worse, all right? Go learn some quantum stuff. Go study this at university. We need more people in it, and it'll get even more mind-blowing. This is the tip of the iceberg. This stuff is beautiful. It touches on what we think nature. We think there's some truth to it because guess what? Planes fly, computers work, and we wouldn't have these things if we didn't have beautiful quantum theory, which gives us, close to 12 to 14 decimal places of accuracy with crazy calculations. So get involved. There's only so much I can sort of tell you here without math, because all of this stuff is described via math. They represent physical concepts, but unfortunately, when you start merging together heaps of physical concepts that don't relate to anything physical, what I mean by that is these physical concepts don't always relate to things that they don't always have analogs to human sort of reality. So spin, it doesn't have an analog. Quantum fields doesn't have an analog. It's not the same as just a wave or something. So that's why you can't approach these things without the math. The math is, the concepts in there. There's no concepts. There's no physical things that correspond to it. And so building up a physical picture sometimes is not possible without the math. Basically, I'm creating this new kind of VPN called a post-quantum VPN. It's literally got these things in it called post-quantum algorithms. And they can actually theoretically defend against a quantum computer, because a quantum computer wouldn't even be able to break this encryption. The math problems in them are so hard. And so you can use it for free right now. So if you want to come use it and support my channel and this YouTube, you can do that by using this. Dude, how are you going to communicate all this info? I know, sorry. Let's keep going.
Of about 2,200 kilometers per second. Fast enough to get around the Earth in just over 18 seconds.
Why does the energy of gluon interactions bring forward mass? That seems counterintuitive to me. Yes, that's really complicated, and that is literally like, advanced quantum field theory. Too deep? Sorry. We'll cut some of that out probably for the video.
Like quarks, we think electrons are fundamental particles. 99.99999999999% of an atom's volume is just empty space.
Except that this is where the probability cloud stuff comes in, all right? So it's not actually empty. You've got this stuff that is in a superposition of being in these places. So it's technically not empty until you take quantum measurements of these things and collapse the wave functions, which are permeating these areas. So keep that in mind. You'll hear people say everything is mostly empty space. Not true. Not true, my friends. Everything, quantum fields. So why, like, you might think all of this was kind of pointless to talk about. No. Quantum field theory, which is what the standard model of particle physics is, right? So to go even deeper than just basic quantum mechanics is you get to this place called quantum field theory, and everything is quantum fields. Particles like electrons have a corresponding quantum field, and everything is just quantum fields, and all particles are excitations in this field. And so if everything's just quantum fields, everything is like, so every particle has a corresponding quantum field, and they're all superimposed on top of each other. And so to understand how this stuff works, which we're talking about, is to understand how quantum fields work. And to understand how quantum fields work is to understand how our world works, because our world is just mixing and fluctuating quantum fields. So if you kind of ever want to try and approach what's going on around here, you got to understand this stuff. Otherwise, you'll never even get close. But the only way you can do that is if you go study physics.
Except that it isn't.
Because you've got all these quantum fields everywhere, right? And they've got these quantum fields have wave functions, and they've got all this stuff going on, right? And it's always constantly bubbling and moving, and there's virtual stuff happening, right? So it's not empty space. It's technically has non-zero probabilities of things being everywhere. So you'll hear a lot of scientists who've never learned quantum field theory talk about how, it's just mostly empty space everywhere. Not true. Even in empty space, where there's meant to be nothing, literally nothing, guess what the quantum fields are doing? They're bubbling. This is what you call the quantum form. You still have stuff, even when you have nothing. How does that make sense? Go ask fucking physicists.
We perceive as emptiness is actually a space filled by quantum fluctuations, fields that have potential energy and build and dissolve spontaneously. These fluctuations have a fundamental impact on how charged particles interact, but that's a topic for another video. How much space do the core and electrons actually fill? If you were to subtract all the spaces between the
Hold on, is that me? Ellie? No, it's just someone who kind of looks like me.
atom cores from the Empire State Building, it would be about as big as a rice corn. All the atoms of humanity would fit in a teaspoon. There are extreme objects where states like this actually exist. In a neutron star, atom cores are compacted so densely that the mass of 3 suns fits into an object only a few kilometers wide. By the way, what do atoms look like? Well, kind of like this.
So here you've got the orbitals, right? So this is where you're likely to find the electron. But guess what? It also is a non-zero probability of being elsewhere as well, and everywhere else in the universe for that matter. But look, this is where you're probably going to find it.
Electrons are like a wave function and a particle at the same time. We can calculate where an electron might be at any given moment in time. These clouds of
when you go into quantum field theory, everything is just wave functions and quantum fields. So keep that in mind.
Probability, called orbitals, are where electrons might be with a certainty of 95%. The probability of finding an electron approaches 0 the further we get away from the atom core.
But it's non-zero.
But it actually never is 0, which means that, in theory, the electron of an atom could be on the other side of the universe.
Yes.
Okay, wait a second.
Good meme.
These strange thingies make up all the matter in the universe. For many dozens of known elements, you don't need many dozens of elementary particles, just 3. Take 1 proton and 1 electron, and you have hydrogen. Add a proton and a neutron, you have helium. Add a few more, you get carbon. A few more, fluorine, even more, gold. And so on. And every atom of an element is the same. All hydrogen atoms in the universe, for example, are the same. The hydrogen in your body is exactly the same as the hydrogen in the sun. Do you feel confused right now? We certainly do. Nothing on this scale of the universe makes any sense in
a Pokemon belt.
Our world. And we've not even begun talking about quantum mechanics or the particle zoo, which are even stranger. Our model of atoms has changed a number of times since we first conceived it.
Hey, look at all these. Beautiful. So we were talking a lot about the Bohr model. Yes, there were earlier ones, but that was before we even knew about some of the particles down there. Rutherford and Thomson famously discovered, what's it called? So I can't remember which ones they specifically discovered, but you got to remember Thomson, Rutherford was a student of Thomson. So I think Thomson discovered the neutron, I think it was, and Rutherford discovered the proton, I think, or was it the other way around?
And the current one will certainly not be the last. So let us support scientists and research and wait
No
for
one
the
knows,
next
bro.
wave of mind-boggling new information about this strange world that is the basis
It's gonna change.
for our existence.
Oh, look, they've got their team up. Wow. Thank you, Philip, Stephen, Thomas, Stephen, Martin. Oh, fun fact, I was walking around the city the other day and someone was wearing a Kurzgesagt top. These two old guys. And one of them turned back and looked at me, and I was like, I wonder if that guy is involved with, like, creating Kurzgesagt stuff. No shit, this happened in the city. And I was like, I wonder if he's seen my YouTube videos. And that's why he turned back. He was wearing, like, a full-on Kurzgesagt shirt. And it was just the logo. And I was like, hang on, that's Kurzgesagt's logo.